Here we go with the long-promised analytical skills video. I am going to show you quickly the CAM document, which is the Curriculum Assessment Manual. We're going to use all of these points as basically a tick list just to make sure that we cover everything in this video. Moving on straight away, SI units. Hopefully you know these by now, but there are only 7 of them. Please learn these. Just make sure that you know them off by heart, because they are the only base units that we have in the universe for now. And the symbols, please, also, please make sure that you know the difference between what a quantity is and what a unit is, because often these are in a multiple choice question, and although T, for instance, would be a symbol for the quantity of the base unit, it's not the symbol for the base unit. So read your question carefully and make sure that you are doing the right thing. Is it the quantity of the base unit that they are asking for, the base quantity, or is it the base unit? And then the only other thing I need to remind you of here is that this last one, there's not really a topic in further studies physics where we use the luminous intensity, the candela, the CD, but you need to be able to recognize it still as a base unit. Please do not confuse it for luminosity. Luminosity is not a base unit. If you look at the definition for luminosity, it's the energy emitted per second. So if you're thinking about energy per second, so that's basically work or energy over time, which is power. And that is definitely not a base unit, because that is measured in watts, which is not a base unit. So it's not a base quantity, I should say. So there are some derived SI units. They are not base units, but we use them all the time, like Newton, joules, hertz, Pascal. There are others. I just snipped these in here that I can quickly use them, because then you are expected to take these derived units and make them into base units. So if we just look at Newton quickly, what I always do is I just take an equation from the information sheet, or one that you know is definitely right. You all know F net equals MA, and then you know the unit for, I also would advise when you're going from quantities to units, don't say that they are equal, because kilograms not equal to mass. It is the unit of mass. So use another symbol, or go therefore, or put the arrow like I've put it now, is then going to be kilograms, and you know acceleration is in meters per seconds squared, and done. There's our derived unit in terms of base units. If we do it for energy or work, the easiest one to remember you can use any equation on the information sheet, but the easiest one, short and sweet, is work is equal to force times distance. And you don't have to worry about when we're looking at the units. I know it's perpendicular distance, but you don't have to worry about that here. Force is still, we've got it now, but you can still say, if this was not if you didn't have force already, so you're going to say MA and then delta X. And then it's easy to put the units in there. So that's going to be kilograms, meters per second squared again for acceleration, and meters for delta x. If you use an S, it really doesn't matter. And then when you combine those, it's kilogram meters squared seconds to the minus 2. Please write it together. That would not give you, I don't think that would give you the final mark. Combine the meters together like we've done here. I'm going to do the other two very quickly, because hertz could pop up in an oscillation question. There are a few equations again that you could use for hertz. Hertz is frequency, which is, you get an equation on your core physics that says 1 over t, which is the period. So that's going to be, if you change it into units, 1 over seconds, which gives us seconds to the minus 1. And if you know your wave physics, you will know that frequency, or hertz, is just per second, because it's how many things happens in 1 second. Oscillations, circles, whatever it is, how many happens per second. There's also other equations. You can use the wave equation. V equals F lambda that some of you will also do a little bit later, and then you can say, okay, meters per second is the unit for speed, and then we've got our frequency, and then we've got lambda is in meters, and you'll see that you end up with the meters cancelling out, and then the unit for frequency would then again be seconds to the -1. So it doesn't matter which equation you use. And then Pascal is one that we don't really work with often, but pressure, you should really know, is force per unit area. Force we've done now, so I'm going to cheat and use that. Kilograms meters per second to the -2, and then you know that area is in meters squared. So that will just give us kilograms meters. That one of those will cancel out, so we get meters to the -1, seconds to the -2. If you swap these around, it's not really a train smash for further studies, because you'll get a mark for that. All right, luminous intensity. Remember, we're not using, but if you look at luminosity, the power one, I'm just going to do it here in case. So power is the work over time. So if you look at that, that's going to be F again, which is MA delta X, which we've done now, and then over the time. And if you put that into units, you'll see that the base units for luminosity is then actually going to be kilograms. We've got the meters per second squared there, then we've got meters, then we've got seconds at the bottom. I'm doing it fast because we've done this now already, and that would then simplify to kilograms meters squared seconds to the -3. So that will be power or watts in terms of base units. Definitely not a base unit, as you can see here. So that's the base units for luminosity. All right, then we get to homogeneous equation. Let me clean this quickly. We get to the homogeneous equation. So the only thing you need to do for that is to basically say what is the equation homogeneous. I'm just thinking I forgot this one. Why did I actually have here? This is an equation that is on your information sheet. So often for base units, they could also ask you give the constant, or give one of the quantities here, the base unit of that quantity, and often it is a constant. So if they say derive the base units for G, for instance, then please start from base principles. Don't just shove values in there. Show them that you know what you are doing. So you're going to write that equation then with G as the subject of the equation. Show the steps. You'll see in the front of the paper it says final answers doesn't necessarily get full marks, because here it wouldn't, because you're not showing that you know what base units are if you just write the answer down. Because I know this is on the information sheet, we know that, but you need to show using base principles that this is actually going to give you that correct one. So then you're going to say G R squared over M. Hope my algebra is correct there. And then again, changing it into base units, G is an acceleration, which is meters per second squared. R squared is meters squared, and then we've got a big mass at the bottom. Don't get your M's confused when it's mass or meters. That's also why it's good if you show when you're changing from quantities into units. And now we can simplify that into, now you'll see the meters is actually going to become 3 to the power of 3. I would still put the kilograms in the front, but it's got a negative power now, so it doesn't matter if you put it at the end. Seconds to the -2, and then kilograms to the -1. We normally put the positive powers first and then the negative powers, the rule of thumb. Then for homogeneous equations, you will do basically this on both sides of the equation, and make sure that both sides of the equation is then going to give you. So if I was going to do it for this one, I could say, oh, let me leave those units for G, because you would have that on the information sheet, and then you can say, okay, G on this side is an acceleration, so it's meters per second squared on that side. So please don't say that it's equal. start by saying left-hand side, do the units on the left-hand side, then say right-hand side, because if you're proving whether it's homogeneous, you cannot just from the beginning say it is homogeneous. You need to prove what the question is asking you to prove. Now we have the units for G. If you had a question like this, it would be from the information sheet. Kilograms there to the -1. And let me just clean this up. And then we would have the M there, the right hand side, which is kilograms, and immediately you can see that those two would cancel out. R squared is meters squared, so 2 of those will cancel 2 of those, and we end up with the unit here. And you can show it like this. You can do it in pencil. We like when you show what you are doing. So that will give us meters per seconds to the -2 as well. And now you can say, therefore, they've got the same base units, and therefore it is an homogeneous equation. Okay. Please remember that a homogeneous equation doesn't necessarily mean that it's a valid equation, because you can get an equation. You can say E equals half mv squared, and then you will, if you do this, it will be homogeneous because you'll have your joules that we've done earlier, and you'll see that the units on this side and the units on this side is going to be the same. But if the half is not there, it's not actually a valid equation. And remember, halves, real numbers, don't have units, so they are, we call them dimensionless. They don't have any units, and therefore they will not affect the equation. I just put the equation of motion in there so that you to remind you that if there's a plus or a minus in your equation, then you must remember to do the base units for every single term. So if I was going to do it for this equation, I'm just using that one quickly. Remember, you can get both versions, it doesn't matter. Velocity would then be meters per seconds, but then that whole thing is squared, which would give us meters squared per seconds to the -2. That one would be the same, but show base principles again. Show how you get there. Don't just assume that they know you are on, that you know what you're doing. Show your steps. Acceleration is meters per seconds squared, and then we've got the meters there, which is going to give us meters squared per seconds squared again. So if you have an equation that has different terms, every single term must have the same base units. Moving on. Uncertainties. So for uncertainties, there are 3 ways in which we can ask you to write it. So this is just a simple example from, I think it was from Siavula. I did put the sources there in the beginning. You can go and have a look, and I've put the YouTube videos that I think you could find helpful on these pages as well, and on the classroom. Absolute uncertainty is, now remember when we're taking a reading, if you're looking at this one, you're not 100% sure. I'm going to go a little bit fast because you know these things. You're not 100% sure where that reading is. It could be there and it could be there, but it could also be halfway. So what we normally do with an analog meter is we're saying that it's half the smallest reading, especially if there's a nice little gap like this. Half the smallest reading. So in this case, the plus minus will be half a milliamp. So we would say plus or minus, and please make sure that you write these down correctly. So the smallest reading there is the smallest reading is 0.2 milliamps. If you look at the intervals here, it's 0.2 milliamps, so half of that would be 0.1 milliamp. So when you're taking your reading, you take your reading and then you say plus or minus 0.1. So that's the absolute uncertainty. Oh, very, very important. Make sure you write this properly. You're not going to put milliamps with the ampere, I should say, at the reading and at the unit. That's why I actually like putting the brackets. So I would like to say 1,6 plus or minus 0,1, and all of that, the unit for all of that is milliampere. So that when you have powers of 10, you would also do that. You would say times, we could actually do it for this one. We could write it as 1,6 times, now forget about my error there, plus or minus 0.1 for my uncertainty, and then I say times 10 to the minus 3 ampere. So the power of 10, I don't write it for each of these, and please make sure that they must be to the same power of 10, definitely not to different powers of 10 there. The fractional uncertainty is then just giving the uncertainty as a fraction of your actual answer. So in this case, it would be 0.1 over 1,6, which would then simplify to 1 over 16. We don't often write it like this, but it's fine, it's still correct, it's the fractional uncertainty. The percentage one is more common, where you just take the fractional one then and times it by 100. Be careful when there's an uncertainty on both sides. So in this one, we're assuming there's no zero error here, but if you were taking the length of something, there's often a question where you are measuring the length, especially in thermal physics, there could be a length. If you're looking at this one for a thermometer, there's no zero error there because the liquid is filled past the zero. But if you're taking the length here, there's a plus minus here, and there's a plus minus here. If you look at this, the smallest reading here, the smallest value reading that you could take is going to be 1 millimeter. So it's plus or minus 0.5 and plus or minus 0.5. But then that uncertainty is on both sides. So you need to add it on both sides, which means that you're going to have 2 times the 0.5, which becomes 1 millimeter. So you'll see when there's a double measurement where you're measuring from both sides, actually the uncertainty becomes the smallest reading. I just threw this in here so to remind you that if you are doing volumes, you must make sure that you read at the bottom of the meniscus, or if it's something like mercury and it's curving up like that, it would be at the top of the meniscus. But you need to account for the meniscus. So this could be an error, which we are going to get to just now. Significant figures, please, you know the rules. The zeros in the beginning never count. So these ones, they are not significant. Zeros in between values are always significant. So please remember that they're always significant. Values that are not zeros are always significant. And then zeros at the end that are not followed by values, they are not significant. So for this value, we would have 1, 2, 3, 4 significant figures for this example that I've got here. So please remember that you must give your answer to the correct number of significant figures every single time. It's going back. So I'm going to throw that one out just to give us the examples quickly. When we are calculating, with values with significant figures, please remember when we're adding and subtracting, we look at the decimal places. So it's the least number of decimal places, because this value, you couldn't read any more decimal places. If this was a piece of apparatus, remember it's guided by our apparatus. There's nothing here that I could read. So when I give my answer, I need to give it to the same number of decimal places as the least number of decimal places, because we're adding the same thing, kilograms adding to kilograms. Remember, you can't add apples to bananas. So it's always going to be the same unit that you're adding. Make sure that they are the same unit. But when we're multiplying or dividing, then we're going to use the least number of significant digits, because you couldn't, again, that value was significant up to that point, but there's only 2 significant figures, and therefore our answer will have 2 significant figures. It would be better to give this answer in scientific notation, because if there's a lot of zeros, that just doesn't look neat. So we would rather say, if you're looking there, that would be 5,7 times by 10 to the minus 4. That would be a better answer, and then you would put your unit, whatever it is. I said kilograms, so let's just stick to kilograms. All right. So the rules I've just put up there, but I've spoken through it. For significant figures, so I can throw that out. This was just an example from the video that I've loaded there for you, but you can go and watch it. He goes through the steps one by one with plenty examples. If we're looking at random and systematic errors, not going to spend much time here. You've done this for many years now. Random means that a random error would cause the value to differ in all kinds of directions. So you could have a smaller than real, bigger than real. So what we're saying real is if you're on the dot there, if you got the correct answer many times and your value only differs a little bit up and down from the real value, then you know there's no error. If there's up and down a little bit further from your real value, then there could be a random error. But if all the errors are lying to one side, then you know it is a systematic error. You've done this a lot of times because actually you've done it when you did precision and accuracy. So it's kind of linked to precision and accuracy. Precision would then mean that if a value is very precise, it would mean that all the values are close to each other, so the range is very small. Use the correct words when you're explaining this. And when the accuracy is very high, it means all your values is correct to the right value. But it doesn't always have to be scattered in the same point. So it doesn't have to be precise and accurate. So this value is precise and accurate because they're not far from the real value and they are close together. Here they are not close together, but if you get the average, and that is important, you always need to get the average of your values. If your average gives you the real value, yes, then the value is you've got an accurate value because it's giving you the correct value, but it's low precision because the range is big. And then this one is just bad. They're all to the one side, so that means they're not accurate, and they're also not precise, they're not close together. Like I said, you've done this a few years in a row now already, so that should be pretty easy for you. Just when you get a question like this in the exam, I said it the other day, please be very specific when you are looking at an answer. This was the question from a past paper. Which type of error do you think you've made? And give a reason. So if you say that it's precise, say that the values are close together or the range is small, something like that to prove that it's precise. Or if you are saying that it is accurate, say that the average gives you the real value. And you can't speak about accuracy if you only have that one value, because you can't get an average. Remember that. Then we have random and systematic errors. Again, the reason why I put these in here is so that we can talk about how to make them smaller. So if you have a random error to make them smaller, averaging would not give you the mark. Averaging the repeated readings, if you're averaging 1,000 and they still have the same range, you're going to get the same value. You're taking repeated readings and you lose the outliers. Please remember, look for outliers and eliminate them. Okay, so eliminate the outliers and then you get a new average, and that would give you a more precise reading. It still might not be accurate though. Accuracy, if all your values are lying to the one side, it doesn't matter how many you take, you're not going to improve the accuracy. So repeated readings is not going to help for a systematic error. So please, that one is difficult to reduce, and often you have to then compare your apparatus with another apparatus that is correctly calibrated. Check the calibration, check the zero reading. And if the question asks about a systematic error, a specific systematic error, what systematic error have you made? Then make sure you are mentioning a systematic error. Or if it asks for what random error could you make sure that you answer in terms of a random error. I hope I'm still within my 20 minutes. I'm not sure. Then for calculations with uncertainties, I'm going to go through the rules fast. I also have put another video here for you with a lot of examples on how to deal with this in calculations. What you need to remember, if it's a plus or minus, then you have to add the absolute uncertainties because it's in the same unit. Make sure they are in the same unit, and then you add the absolute uncertainty. Multiplying or dividing, you have to, because they're now not in the same unit, the one is meters and the one is seconds here, as you can see there from that example, then you have to make sure that you do the fractional uncertainties or the percentage uncertainties. I see some people are just more comfortable with calculating the percentage uncertainty, but then just remember to go and give the absolute uncertainty in the end again. And make sure that you're writing it properly. So here you can see the values were given to you as there's 3 significant figures. That one actually had 2. So I would say that your answer here should have been to 2 significant figures. They didn't obviously focus on that for this example. But if you're looking at significant figures as well, the significant figures must be the same as the least amount. And then when you go from value to uncertainty, you look at the same decimal places, because you can't have a more accurate uncertainty than your actual reading. And then when you've got a power of remember, for this one, it's a little bit small there. I'm just going to make it a little bit bigger for us. If we're looking at powers here, that could have been R times R times R, which would mean we're adding the fractional uncertainties. So it's 3 times that same fractional uncertainty, and that is why it's 3 times the fractional uncertainty. So the power becomes the factor that you multiply the uncertainty with. And then just remember, if there's any weird thing or you are not sure, a method that could never fail is when you are, I think this is it, when you have something like cos or tan or logs or something in your calculations. Just remember this for future. You can always take the maximum value minus the minimum value and then divide them by 2. Because if you remember your uncertainty, if you have 5 plus or minus 1, the biggest value it could be is 6, and the smallest value it could be is 4. So that's your range. So if you say 6 plus 4, that would give you 10. Divide by the 2, that would give you your real value. And if you take your uncertainties, so biggest minus smallest divide by 2 will always give you your real value if you then minus that from your uncertainty. So please, that is a fail safe. If all else fails, take your biggest value, max, minus minimum, divide by 2. Will still give you your uncertainty, especially if it's not linear, if there's signs or cos or logs or something there. And then, very important, make sure you write your answer correctly. So if you have, I'm going to try and, let's do this faster, this one here, the one is given to you as just the random answer, and then there's your uncertainty. But this is now times 10 to the minus 3. You cannot do this if they're not both to the same power of 10. So that one there is going to be, if you're writing it to 10 to the minus 3 as well, 1, 2, 3. So that's going to be 2,346 times by, or plus or minus 1,623, and all of that will then be to the power of times 10 to the power of minus 3. And please, we don't use that unit at all. It's not sec, it's seconds. So seconds, and just an S. I just snipped this from a random worksheet. And then the same there, the powers of 10 cannot be different. So if this is to the power of 22 and that's the power of 20, then you need to make sure that they're the same power of 10 before you write them in. The same same power of 10 and the same significant figures before you write them in. So I'm just going to do that last one for the maths again. For this one, you would then say 9,11, 3 significant figures, plus or minus 2,23, and put that in brackets, times by 10 to the minus 33 kilograms. Make sure you write your answer properly. And I think I'm going to have to make a second part for the graphs, because I think my 20 minutes are up.